Last time we were discussing the position vector, and then we were discussing essentially the derivative of this vector. This position vector for a moving object, this position vector keeps on changing with time. Okay, so for a moving object, then if you want to talk about the rate of change of this position vector, you then talk about the derivative of this vector, which is of course a vector v. Okay, so this of course in general also depends on time as the object moves. V physically tells you something about the direction of motion. If you know v, you know essentially where the object is a short time later. Okay, so you have your rate of change of your position vector, which is the velocity vector, and from this vector you can figure out the acceleration vector, right? So the velocity vector is given as the derivative of the position vector. What do we mean by this? We mean of course that you consider the position derivative at time t, you consider the position vector at time t, position vector at time t plus delta t, take the difference, divide that difference which is a vector by delta t, take the limit that delta t approaches 0. What is it good for? It tells you essentially how quickly the position vector is changing. It tells you if you know the velocity vector, you can then immediately figure out in which direction is the object moving. If you know the velocity vector, you know where the object is a short time later. If you know the velocity vector, you know how fast the object is accelerating, because then you can figure out the acceleration vector. So the velocity vector tells you many things. Okay, right? How to actually calculate this derivative in practice is very straightforward. You basically just take the derivative of each of the components. So this thing is actually just the x component of the position vector, differentiate that, take the y component of the position vector and differentiate that. That's the velocity vector. Okay, that's how you compute the velocity vector. Okay, it's just the vector of the derivatives. So in the same way you can find out the acceleration vector from the velocity vector, because this is completely general. You can consider the derivative of any vector. The derivative of any vector is always the derivative of its components. Okay, in the unit vectors Ex, Ey, and if need be Ez. Okay, in your calculus 2 course, you learn that it's not as simple as that always, but for this course this is always true, that if you want to take the derivative of some vector, you just differentiate the components. Okay, anyway, so you have that the acceleration vector is just the x component of the velocity, differentiate that, plus differentiate the y component of the velocity. And of course this goes along with an Ey, okay, or y hat or j hat. There's something about notation that I should mention. The position vector is special in the sense that the x component of the position vector, we just call that x rather than r subscript x, and the y component of the position vector we simply call y rather than r subscript y, just for simplicity, because the position vector's components occur so often that you just simply call them x rather than putting subscripts. Okay, for almost every other vector you put in the subscript. So if you're talking about the x component of the force vector, you write f subscript x. If you're talking about the y component of the force vector, you say f subscript y. If you're talking about the y component of the linear momentum, मुझे भी दिखा दो क्या दिखा रहे हो, कौन सी इतनी अर्जेंट चीज़ है यार. If you're talking about the 18 साल से बड़े हो गए तो 18 साल से act like it, okay. If you're talking about the y component of the linear momentum, you say p subscript y and so on and so forth. The position vector is an exception, okay. So you don't write r subscript x, okay. You just write x, okay. Anyway, so let's apply this. The first application we'll do is so-called circular motion, and in particular uniform circular motion. Okay, so you have an object that is rotating in a circle, and of course the special thing about an object that is moving in a circle is that its distance from a fixed point is constant. That's what it means to have a circle. That circle is a set of points such that for every point in this set of points, the distance from a fixed point is the same. That distance, of course, being the radius of the circle. Okay, so you imagine an object, you imagine a movie of an object moving in a circle, and you take a picture of this movie, and in this movie what you see, in this picture what you see is, of course, I've just drawn in dotted lines. You don't see these dotted lines in the picture, of course. You see the object, for example, over here. Okay, and you can also label this fixed point, this point from which at every time the object is at the same distance. So that point we label it somewhere over here, of course. Okay, and you want to use the property essentially that this object is always remains at the fixed distance from this point. So you want to use this property. So if you want to measure the distance between 2 points, of course you have to do what? You have to take the difference of the x coordinates, square them, take the difference of the y coordinates, square them, add them, then take the square root. You get the simplest description, mathematical description of the distance between these if, where do you place the origin? Where should I place the origin? At the yellow point. Because then this special point from which I am measuring distances becomes the origin. If I place the origin somewhere else, which I could do, there is nothing illegal about doing that, but then I will have to constantly consider the coordinates of this point as well. When I place the origin over here, I don't need to consider the coordinates of this point because these coordinates become trivial then. These are just 0, 0. Okay? So it's suitable that you essentially choose your axis like that. Okay. Again, you can choose the x-axis to be pointing that way. You can choose the y-axis to be pointing that way, but that doesn't really lead to any advantage. So let's stick to the conventional choice. And now the object is over here, so let's draw a line like that. Okay. And as the object rotates, let's call this distance capital R. As the object rotates, अगर if मैंने को 2-3 टीए बुलाने पीछे और मुझे तरफ से पूरी अथॉरिटी को थप्पड़ मारे वो, फिर ना मुझे कहना ओके, पीछे वाले बैठ के इतनी इरिटेशन होती है ना सच्ची भाई, इधर आके सुनो जरा. You think कि मुझे आपके घर के हालात नहीं पता चल रहे, सारे पता चल रहे होते हैं. ओके, so as the object rotates, what changes? This distance capital R does not change as the object moves in a circle. So what is changing in its motion is actually not the x coordinate. The x coordinate is changing, the y coordinate is changing, but they are not changing independently of each other. If you know the x coordinate, you know the y coordinate because the object is moving in the circle. Okay, so x and y in other words are not independent of each other. You know one of these, you know the other. And you can see that straight away from here. If I know this angle theta, once again I make the conventional choice that I choose to measure the angle with the positive x-axis. If I know theta, I automatically know the x coordinate, I know the y coordinate. In the physics language, we say that this system has 1 degree of freedom. Essentially, you need to know only one number to specify where the object is. You need one number to specify the state of the system, so to speak. Okay. Anyway, so you write down then that the x coordinate is r cos theta. That is easy. Y is equal to r sin theta. Of course, there is nothing new over here. This is just using the definition of the sine and the cosine. Okay. And then you can write down the position vector of the object at this instant of time. So you have r cos theta ex plus r sin theta ey. And now this was a still picture, remember? And now you think about what happens as the object moves. Okay? As the object moves, this becomes, of course, time dependent. The object is found at different positions as the object moves. That's the very definition of motion. Okay? So this capital R does not change because the object is moving in a circle. That's a basic assumption to begin with. Okay? So all the time dependence must be carried by this theta. As the object rotates in this circle, theta changes, of course. Okay? So in general, we write down that R as a function of time t must be of this form for uniform circular motion. r of sine of this angle that depends on time in some way. Okay, right. Now, अब क्या करेंगे? Now, if I ask you, okay, well, describe how the object is moving. Well, to describe how it's moving, you can say, of course, that it's moving in a circle. Okay, mathematically, how can I prove now from this vector that it's moving in a circle? You just calculate the magnitude of this vector. The magnitude of this vector measures the distance of the object from the origin. If the magnitude of this vector remains constant and you expect the magnitude of this vector to be capital R always, then the object is moving in a circle. Let's check whether the magnitude of this vector is capital R, okay, right? Because R without the arrow is often used for many other things, for example, a radius or something like that. It's typical that you denote the position vector, the magnitude of the position vector by two vertical lines, okay. So that's what it means. The magnitude of the position vector. If you put in a vector between two vertical lines, that refers to the magnitude of your vector, okay. This is equal to, okay, how will I calculate this? I scale the x component, I scale the y component, I add them up. That's basically Pythagoras theorem. So you get r square cos square. I don't even need to worry about how theta is changing with time, okay, plus r square sine square theta of t, and then you have the square root, of course. R square you can factor out from inside, what is left is cos square plus sine square, and cos square plus sine square, no matter what value of theta you have, cos square plus sine square will always be equal to 1. So you're left with square root of r square, and square root of r square is simply r. Okay, so that's how you check whatever you are doing. Check whether everything continues to make sense or not. Okay, right. The next thing I have to do, okay, so if you want to describe motion using this position vector, but I figured out that this position vector implies that the object is always at the same distance capital R from the origin. But how is it moving? It's moving in a circle, sure, but is it speeding up as it moves? We know as it moves in the circle, the direction of the velocity vector keeps on changing. But maybe the object is also speeding up. Maybe the magnitude of that velocity vector is also changing. The velocity vector, remember, is always tangential to the path. But that doesn't say anything about the magnitude of the velocity vector. Okay? So to answer this question further, I need to know something about what this function theta of t is. How is theta changing as a function of time? What's the simplest non-trivial function that theta could be? Of course, the simplest function would be that theta is just a constant. But if you put in theta equals to constant, what do you see? The object is stationary. There is no time dependence then. The object is just standing still. Okay, so let's go to the next more complicated case. What's the next more complicated function? A straight line with some non-zero slope. Okay, my disappointment always knows no bounds, okay. Okay, so you have theta of t is a straight line. That's your next more complicated function. What's more complicated than that? A quadratic function. What's more complicated than that? A cubic function. Well, you don't need to go to quartic function, basically. You basically get the point. What's more complicated than that? You basically go to Taylor series and say that I sum up over all these functions up to infinity. Then you basically get exponential functions. Okay, and if you peel off some of those powers, you get the sine function. If you peel off some other powers, you get the cosine function. Remember the Taylor series? That's how you define. You go from the simplest function to more and more complicated functions. Anyway. So in this case, I just have that it should be a straight line with some slope. What's the equation for a straight line with some slope? Now, of course, आपने तो y is equal to mx plus c बताना है, but in this context, how will you write that down? Probably omega t plus some constant. Omega is essentially d theta by dt. Omega is the gradient, is the rate at which theta is increasing with time. And because this is a straight line, this is a constant rate, omega is a constant. So this omega over here is a constant, which of course अगर आप इसको calculate करो d theta by dt comes out to be omega. So omega is also called the rate at which theta is changing, aka the angular velocity. Okay. So you have this as theta. This is your simplest non-trivial possibility for this function that allows for motion. That's why you always do first of all uniform circular motion, because that's the simplest scenario. उससे ज़्यादा simple तो motion ही नहीं होता. Okay, right? So, and what is this phi? इसका physically क्या मतलब है? Well, let's come to that. ये theta of t plug in कर दो उधर. So let's plug it in. So r of t now for this special case becomes r cosine of omega t plus phi ex plus r sine omega t plus phi थैंक यू. यूनिट वेक्टर मुंह से निकाल दिया करो. मुझे पता है आपके मुंह से निकलते हो यूनिट वेक्टर का नाम जो है आपको शर्म आती है. आ रहे हैं उस तरफ. आई एम जस्ट सेइंग दैट दिस इज अ straight line. So in general a straight line will have some intercept, right? ये general. Of course omega t इसका special case है. For that case phi is 0. Okay, so if I write down that d theta by dt is a constant, another way to understand would be that if I say d theta by dt is a constant, what is theta? You say, well, the solution to this differential equation is that. That's the general solution. Phi of course मुझे पता कोई angle है, because theta is an angle. Okay, but physically वो angle क्या है? I've used this Greek letter phi because I know that this is an angle. Okay. Now from this can you figure out phi? मैं आ ही रहा था यार उस तरफ. Okay, so from this can you tell me कि phi physically क्या है? If I say कि भाई okay, design an experiment that allows me to measure the value of phi, क्या करोगे? You essentially look at where the object was at the instant when you started your clock. That gives you the value of phi. It's not a very complicated experiment. And different people will measure different values of phi depending on when they bother to start the clock. Because at t is equal to 0, it's always the same thing. Remember वो x naught क्यों आया था? What is the x coordinate of the object at the instant when you started your clock? It's the same thing over here, except that instead of the x coordinate, now you're talking about an angle. So r at t is equal to 0. R क्या आ रहा है? Cos phi ex plus r sin phi ey. What is this? The x coordinate. What is this? The y coordinate. This is the initial x coordinate. This is the initial y coordinate. तो ये phi क्या है? The initial angle that the object is making with the positive x-axis. As in आपके पिक्चर के अंदर जो आपने स्नैपशॉट अगर ये t is equal to 0 पे बनाई होती, ये वाला एंगल क्या है? ये phi. If you made the snapshot at the initial time. Okay. Right. Now the beauty of this is of course that you can straight away figure out the velocity vector. Given the velocity vector, you can figure out straight away the speed of the object. You can then straight away figure out the acceleration vector just by taking two derivatives. You don't need to draw any funky triangles. You don't need to argue using similar triangles. Of course, you never bother to do that because you never went through the derivations that were presented in your high school books. But if you accidentally happen to open them, okay, and immediately close them in the fleeting instant of time that they were open, you probably saw some similar triangles that were used to argue that the acceleration equals the centripetal acceleration equals v square over r. Okay, that argument is a bit tricky. Okay, but this argument is very, very straightforward. You just take the position vector, differentiate it twice, you get the acceleration vector, done. And from that acceleration vector, you can immediately deduce the magnitude of the acceleration as well as the direction of the acceleration. Now remember, this is only true for uniform circular motion. As in theta increases at the constant rate, equal angles are being swept out in equal intervals of time. I keep on seeing this. I say, okay, you have a hemispherical bowl. Near the edge, you have a marble, you release it from rest. How much time does the marble take? For example, I'm not expecting you to solve this question, okay, but I give you some parameters, some numbers, and they say, okay, how much time does the marble take to go from here to the bottom? Everybody says, well, sir, yeah, this is uniform circular motion. They apply essentially the equation of uniform circular motion in order to attack this problem. This is not uniform circular motion. As the marble moves down, it's sweeping out faster and faster angles. As in omega, as in this angle that the marble is sweeping out, this angle, if you want, this angle, ये जो angle change होता जा रहा है, okay, with this horizontal line, that is increasing at a faster and faster rate as the marble moves from here to here. And then as it moves from here to here, again the rate of change of the angle is then again slowing down. This is not at all uniform circular motion. The whole idea of energy and work and so on were invented to deal with non-uniform acceleration. For example, a block with a spring. It's much easier to attack that problem using energy and work and so on compared to directly trying to attack it using the acceleration. Because the acceleration keeps on changing. अगर आपको simple harmonic motion से थोड़ा बहुत भी कुछ याद है, the acceleration of the block is maximum for maximum extension of the spring. As the block comes back, the acceleration decreases. It's a changing acceleration. It's not a uniform acceleration. Okay. Okay. So now write down the velocity vector. In general, this vector would be a function of time. How do I figure out the velocity vector from this? For simplicity, I'll assume, just to simplify the mathematics, not essential, I'll assume that the object is over here when I started my clock. How does that simplify the mathematics? Phi is 0, because when the object is over here, when I started my clock, the position vector should simply be omega t, position vector की बात कर रहा हूँ, r e x, that's it. Position vector आपका ये है यार, ये देखो ये आपका position vector. Draw arrows to really understand vectors to begin with, okay? Do not consider them beneath yourself, okay? कि मेरा intellect इतना ऊंचा, मैं क्यों arrows बनाऊँ, तो बच्चे बनाते हैं, okay? Draw arrows, that's the arrow. The position vector always joins the origin to the location of the object. मैं कह रहा हूँ object किधर है तो क्या होगा position vector? I mean एक arrow नहीं बना सकते यार. And this arrow is pointing only horizontally. So it's just Rex. The magnitude of this arrow is capital R. So you just have Rex. Rex अगर है तो ये तो आपको 0 चाहिए. So phi क्या होगा? 0. No, in other words, phi is simply the angle that the object makes with the horizontal. इधर क्या angle बना रहे हो horizontal के साथ? 0. There's so many ways to see it. Okay. So just to simplify the mathematics, I am working with the case where phi equals 0. ताकि go back home and do it for other cases. That suppose I started my clock when the object is over here. Then what does the velocity vector look like? अब ये मैं क्वेश्चन कल नहीं दे सकता. Never mind. Okay. पहले मैं यही देने लगा था. अच्छा चलो कोई नहीं, कुछ और दे दूंगा. अच्छा, so you have this, that you have that if the object is over here, phi की क्या वैल्यू होगी? If the object is over here when you started your clock, what is the value of phi over there? 70 किसने कहा? 90 degrees, okay. Okay. So you have that your position vector is then just that. अब velocity vector क्या होगा? इसको differentiate करो और लिख दो. What's the derivative of this thing? So if r remains as it is, the derivative of cosine is minus sine. So you put in a minus, you put in sine omega t. But again, you are differentiating with respect to time. जब आप differentiate, whenever you differentiate, always keep in mind differentiate with respect to what? That may seem trivial right now, because normally you always are taking derivative with respect to time right now, but later on you will be taking derivatives with respect to position, with respect to angles, and so on and so forth. Won't always be respect to time, okay? Okay. Sometimes you might even need to differentiate with respect to some angle. Okay. So anyway, so omega pops out, and Ex remains as it is. That's a constant vector, constant in magnitude, constant in direction. R remains as it is. The derivative of sine is, of course, cosine, and you get omega t, but then when you differentiate, omega pops out, you have Ey. Right? That's the direction of your velocity vector. What is it telling you physically? Okay, the object is moving in a circle. As time goes on, पहले आप ये बताओ, you have made some implicit assumption about how the object is rotating. The way I've written it down, is the object rotating clockwise or anti-clockwise? It depends on the sign of omega, right? Assuming omega is positive, it's rotating anti-clockwise. Okay, so I'm assuming that omega is positive. Okay, anyway. So omega is positive and the object is rotating then like that. So at t is equal to 0, the object wasn't at rest, the object was moving. The object is instantaneously over here at t is equal to 0. At this instant of time, don't look at that. What should be the direction of the velocity vector? Velocity vector ka direction yaar. Anti-clockwise, Ex or Ey, it should just be in terms of Ey. Because the velocity vector is always tangential to your path. For this circular path, given that the velocity vector, given that this is moving anti-clockwise, the velocity vector should be pointing like that. The velocity vector always tells you, okay, sometime later, where is the object going to be? If the object is over here, a very, very short time later, it is over here. What should be the direction of the velocity vector? Like that. Some time later, of course, the velocity vector should have a slight negative x component as well, because the object has to move like that as well. And that's exactly what you see. For t is equal to 0, the x component is 0. For t is equal to 0, sine of 0, that's what you're getting. And for t is equal to 0, you're just getting r omega Ey. And as time goes on, this increases in magnitude. So you're picking up this required negative x component of the velocity vector. That negative x component is precisely what's making it bend to the left. At t, when the object goes from here to here, what's the value of t? This is t is equal to 0. At what time is the object over here? बता दिया ना, t किधर से 90 आ गया यार, खुदा का खौफ करो. I mean, you're telling me t is a dimensionless number all of a sudden. Yeah, yes, okay, 90 over, yeah. So essentially, omega multiplied by t should be 90 degrees, okay, because omega t is essentially the angle that is being swept out, because omega is constant. That's why it's the angle swept out. Okay, it's essentially distance is equal to speed multiplied by time, except in the context of angles. So t is equal to, in terms of radians, pi over 2 omega. If you put in t is equal to pi over 2 omega, क्या मिलता है आपको velocity vector? Pi over 2 omega, omega and omega cancel, you get pi over 2. Sine of pi over 2 is 1. So you just get minus omega r Ex. And this you get cos of pi by 2, which is 0. So your velocity vector at this instant time is pointing only in the negative x direction, of course. Okay? So it checks out. What's the magnitude of this velocity vector? मैं by the way कहा था मैं तेज जाऊंगा, मैं कोई नहीं तेज जा रहा वैसे, लेकिन anyway मैंने और ज्यादा कहीं ज्यादा तेज जाना था. ये ज़्यूम के कि आपने देख लिया ऑलरेडी, पर ऑफ कोर्स आपने ज़हमत ही नहीं की, तो क्या मैं कहूँगा. Okay, so the magnitude of the velocity vector is, how will we find that out? क्या करेंगे? Okay, so you scale the x component, you scale the y component, add them up. You scale the x component, you get omega square r square sine square. Scale the y component, you get omega square r square cos square. You add them once again, you get essentially sine square plus cos square, but that is 1. You're left with square root of omega square r square, that's just r omega. In other words, the magnitude of the velocity vector is always just r omega. Okay? So that's why we say that in uniform circular motion, the speed of the object does not change. It doesn't, as you can see. That does not mean that the velocity vector does not change. That was already obvious from this diagram. At t is equal to 0, that's your velocity vector. At t is equal to pi over 2 omega, your velocity vector is horizontal. That means that you can have a non-zero acceleration vector, because the acceleration vector will only be 0 if the velocity vector remains constant. The vector remains constant. The vector contains both magnitude and direction. So the acceleration vector can be non-zero, and how to check that it is non-zero? You differentiate the velocity vector. So you do, okay, acceleration could be dependent on time. You differentiate this. What do you get once you differentiate this? Sine becomes cosine, out pops another factor of omega. So you get minus omega square r sine omega t ex, and what else? Cos becomes minus sine, out pops another factor of omega square omega. So you get minus omega square cos of omega t ey. क्या हुआ है? Oh yeah, sorry भाई, वो अभी मैंने फिगर आउट कर लेना था. My answers would have made sense, okay? So relax, okay? अच्छा, so you have that. क्या चीज? Because I would have checked the different limits. I mean, to begin with, I know that this is uniform circular motion, so the acceleration vector should be pointing anti-parallel to the position vector. It should be proportional to the position vector. अगर मैंने इधर sin लिखा होता, इधर cos लिखा होता, तो it's not parallel or anti-parallel to this vector. As you will see now, अगर मैं minus omega square को factor out कर लूँ, अब क्या आ रहा है? R cos omega t ex plus R sin omega t ey. And what's this thing in the square brackets? ये अभी भी आपने वेक्टर देखा है, ये पोजीशन वेक्टर है आपके ऑब्जेक्ट का. सो दिस एक्सलेरेशन वेक्टर इज नथिंग अदर देन माइनस ओमेगा स्क्वायर द पोजीशन वेक्टर ऑफ द ऑब्जेक्ट. And what is the position vector? The position vector joins the origin or the center of the circular motion to the object. तो ये माइनस साइन क्या बता रहा है? The position vector is always radially away from the center towards the object. So what's the direction of the acceleration vector? Towards the center, from the object towards the center of the circular motion. That's what this minus sign is physically telling you. What's this omega square telling you? This omega square is telling you about the magnitude of the acceleration vector. What's the magnitude of the acceleration vector? The magnitude of the acceleration vector, of course, is positive. That's just omega square times the size of this vector. जो भी ये वेक्टर है, ये रेसिपी बता रही है, जो भी ये वेक्टर है उसको स्केल अप करो ओमेगा स्क्वायर के साथ, फ्लिप इट. What will be the size of this acceleration vector? Size of this vector multiplied by omega square. But what's the size of this vector? Capital R. Okay, so you just get omega square R. और अगर मैं इस तरह लिखूं, कई लोगों को होता है सर हमने तो दूसरी तरह पढ़ा था R omega square. Okay, it's the same thing. Okay, right? So the acceleration vector is also not constant, by the way, because pointing towards the center is a relative thing. When the object is over here, the acceleration vector points like that. When the object is over here, the acceleration vector points vertically downwards. Okay, in English language, you may consider it to be that the direction is constant. Mathematically, it isn't. Okay, in terms of these unit vectors that you're using. Okay, right. Of course, having done V, the magnitude of the velocity vector, which I did somewhere, there it is, I can simply write that this is just V, because this is constant. This magnitude as in v without the arrow, is not a function of time. It's a constant. So I can form here, ये पहचाना आपने, v is equal to r omega, यार circular motion वाला रट्टा तो मारा हुआ है आपने. And this is equal to, I can say then from here omega is v over r. And I can then plug this over here to say that the magnitude of the acceleration vector is c, the centripetal acceleration. There are a couple of words that for some weird reason हर किसी को मोहब्बत है उसे इस कोर्स में. Two of them, okay. और असल में किसी को उनका मतलब नहीं पता होता. Centripetal और कभी कभी वो साथ में जो आपका ज्यादा स्मार्ट जो दोस्त होता है, सो कॉल स्मार्ट दोस्त होता है, वो उसको अचानक या ख्याल है सेंट्रीफ्यूगल भी कोई चीज होती है. क्या है? I will not mention the word centrifugal in this course, okay, because you don't need the centrifugal force actually. The second unholy word is inertia. जब भी कोई चीज ना समझ आ रही हो, क्यों होता है inertia? क्यों, क्या मतलब inertia का? अल्लाह जाने. Inertia is a measure of mass and mass is a measure of inertia. वाह भाई वाह, अच्छी मुर्गी और अंडे वाली सिचुएशन बनाई हुई है आपने. ओके, अच्छा, anyway, so the centripetal acceleration, the magnitude of this acceleration vector is nothing other than centripetal acceleration. The word centripetal just means towards the center, seeking the center. It is just a reminder for you that in this case the acceleration is pointing towards the center. That's all that it means. It's not a special acceleration, it is not an acceleration on top of some other acceleration. The word centripetal is there just to remind you of the direction of this acceleration vector, that is towards the center of the circular path. That's all it is, okay. So similarly, the centripetal force is there to remind you that this force points towards the center. It may not be an actual force, as in you could say that the total force is the centripetal force. So you have an object on which friction is acting, some other forces are acting, the sum of all those forces, and the object is moving in a circle, the sum of all those forces is the centripetal force. The centripetal force is not a separate force. Just like over here, the centripetal acceleration is not some separate special acceleration, it's just the acceleration of the object. It just points towards the center. So this thing can be written also as r times v square over r square, and this of course leads to one of your very, very favorite equations, which for some reason, actually I know the reason, everybody seems to remember. कहेंगे जिसके फाइनल एग्जाम में 2 भी नंबर आए हो तो उसको ये याद होती है. द रीजन सिंपली बीइंग कि ये ओ लेवल में शुरू में होती है, तो इतनी तो हया होती है कि 5 सालों में इतना तो सीख लिया होगा. सो दैट इज द रीजन दैट एवरीबडी सीम्स टू रिमेंबर दिस. एनीवे, हाँ, that's the magnitude of the velocity vector, that's the speed of the object as it's moving. Okay, so much for that. Okay, disclaimer, ये कल आ सकता है. क्योंकि इधर मैंने कुछ भी नया नहीं किया. कुछ लोग सर आपने एग्जाम्पल लिंक कराई है, क्या कराई है मैंने? There was literally nothing new over here. मैंने पोजीशन वेक्टर पकड़ा, उसको डिफरेंशिएट किया, उसको दोबारा डिफरेंशिएट किया, आउट पॉप्ड एवरीथिंग. अच्छा, anyway, now and this has already been uploaded for more than 1 week now. अगर आप खोल के देख लेते हैं. Okay, the next thing that we have to do, so I need to do 2 things now. In the next 15 minutes I'll do one of those, in the next and the 15 minutes after that I'll do the third one. The next thing I need to do, of course, is to tell you how to go the other way. Given the acceleration vector, how do you find out the velocity vector? Given the velocity vector, how do you find out the position vector? Okay, as in that's really of interest to you. Where is the object at some particular time? So given the acceleration vector, how can I find out the velocity vector? You just take the simplest way in this case would be, you can take the antiderivative, you can look at calculating sums as well. You can look at what you did in 1D. This equation can be interpreted as that, you can interpret it as that it gives you a recipe to relate a small change in something to something else, to the acceleration, in this case acceleration multiplied by the time interval gives you the change in the velocity vector. In other words, dv is equal to a dt. We wrote down exactly the same thing for 1D motion, which of course you have never bothered to actually understand, except that there you didn't see any arrows. Okay. Now I can add up both sides of this equation. So I have from the initial time, which I am considering to be 0, to the time t that I am looking at, और फिर इधर क्या करूँगा मैं? Same as you did in 1D. This is exactly the same. The only difference is that you have an arrow on top of A to denote that now your acceleration is a vector. Again, how you actually calculate this sum is a separate issue. If the acceleration was an ordinary function, you know how to do this. But now acceleration is a vector. And same thing over here. How do I add up this? This one you can almost guess the answer straight away on the left hand side. Because this you are adding up small changes in the vector. If you add up small changes in the vector, what will you get? The total change in that vector. So the left hand side should just be the final velocity, as in the velocity at time t minus the initial velocity, but in this case the vector. So the left hand side you expect it to be, and you can prove that this is indeed the case, that the left hand side will just be that. The right hand side is more troublesome, of course. But then how will we make progress on, okay, how do I actually calculate this integral? When it came to the derivatives of vectors, how did we make progress? Oh good. See, somebody, okay, yes, exactly. You write down the acceleration in terms of its components. Because in terms of its components, the components are ordinary functions. And you know how to integrate ordinary functions. So you always go back to things that you know how to do, okay? You don't keep on reinventing the wheel, okay? Not the meal, okay? But anyway, मैं दोपहर का खाता नहीं खाया था, okay? Anyway, so you have, you go back, you write down the acceleration vector in terms of its components, okay? So you have that you write down, क्या लिखूंगा? आपने तो लगता है 2 दिनों से खाना नहीं खाया. What do I write down? I want to simplify this. इसको मैंने लिखना in terms of its components in a general way. Yeah, thank you. Ax t prime ex plus so you plug this thing over here and what do you see? Remember, Ex and Ey are essentially constants. It's the same vector that appears in every term of this sum. So you can pull out these Ex and Ey outside any sums that they appear in. Okay, so let's do it. This thing becomes 0 to t, you just plug it in. This is exactly what you have done for derivatives, except that you are now dealing with integrals rather than unit vector भूल गया. Okay. Ey and you have dt prime. And now of course you can split up this sum so that this becomes 0 to t ax t prime dt prime ex plus this sum 0 to t ay t prime dt prime ey. Again, most of these things you have already studied when you did 1D motion. The only new things that you are seeing over here are essentially Ex and Ey. And now Ex in this sum, this is essentially a sum of these things. For each of these terms, Ex is the same. So you can pull it outside this sum. Just like, it's basically like, 0.01 Ex plus 0.04 Ex plus 0.07 Ex and so on and so forth. How do you do that sum? आप Ex को factor out कर सकते हो and then you do 0.01 plus 0.04 plus 0.07. Exactly the same way I can factor out Ex and then just do this sum. I can factor out EY and then just do this sum. So this is equal to ये इंटीग्रल करो, उसको मल्टीप्लाई करो EX के साथ, प्लस do this integral multiply by EY. In other words, no big surprise, the integral of a derivative of a vector is basically the integral of its components. Just like the derivative of a vector is the derivative of its components. If you, the only complication here is that for an ordering function you just have to calculate one derivative or one integral. For a vector you have to calculate two derivatives of two integrals, or maybe three derivatives or three integrals. That's it. Okay? There's really nothing fundamentally new over here. It's just double the work. Okay? But work in the English language over here. Okay? Now let's actually apply this. अब ये मैंने theory करा दिया आपको. Now actually apply it, okay, to an example. Okay, there are various examples that you can do, by the way. So as one example, go back home and अगर मैं आपको दूं जो circular motion में हमने acceleration vector derive किया था. If I say this is the acceleration vector, find out the position vector. Make sure that you are able to get the position vector that we wrote down to begin with over there. कि आप उल्टा जा सकते हो. When we did circular motion, I wrote down the position vector and from there we went to the acceleration vector. If I give you the acceleration vector for that case, make sure that you are able to derive, you are able to go back and derive the position vector. Of course, you will be integrating in that case. या तो 1D motion में भी आया था ना. We essentially have time from 0 to t. You chop up your time interval into little pieces. T prime is any arbitrary time between 0 and t. Okay, like I said, most of this notation, that's why you do 1D motion before. Even though, of course, 1D motion is a special subcase of this thing. But if I straight away explain to you this, I'm explaining too much mathematics at one time. To you, I have to explain the function क्या है, you have to explain the derivative क्या है, you have to explain integral क्या है, you have to explain the unit vector क्या है, you have to explain के magnitude क्या है, and so on and so forth. Okay, but I've done it step by step. Okay, so let's apply this. The application that I have, I wish I could show that application by throwing this over there. That would be appropriate. वो भी लिखो मगन है. ये प्रोजेक्टाइल मोशन की डेमोन्स्ट्रेशन में करना चाह रहा हूँ यूं फेंक के ना. बस कर दो. नहीं तो थोड़ा शोर किया करो यार. बड़े हो गए तो यूं बातें लगी हुई हैं पीछे. सुनाई दे रहा होता यार, ना इतना बोला करो. अगर बातें करते हैं बाहर चले जाओ. मतलब 1.25 घंटा है यार. 1 घंटा 50 मिनट भी नहीं है. 1.25 घंटे की क्लास है. 1.25 घंटे के लिए तो चुप कर जाया करो यार. इतनी क्या आपको अर्जेंट बात होती है. वो तो कभी भी लगा हुआ है. Okay. So most of the time, so the circular motion example was an exception. I went from the position vector to the velocity vector and then to the acceleration vector. Most of the time actually you will be going the other way around. From the acceleration vector you will be going to the velocity vector, and then from the velocity vector you will be going to the position vector. The good news of course is that this is relatively straightforward if you know how to do derivatives and integrals. The bad news is that this is considered so trivial that most of the time in this course I won't even be bothering to do this, assuming that you know how to do this. Okay, so for when we go to Newton's laws, I'll stop at writing down the acceleration vector most of the time, and I'll assume कि आगे आप position vector तो निकाल ही लोगे. So this is something that I'll assume throughout the course कि ये आपको करना आता है. Okay, so सर वो final में आ रहा है, pre-mid syllabus आ रहा है final में. I mean, what? I can't ask you in the final exam कि फलाने object का position vector निकालो. I can't ask you कि f is equal to ma apply करो. What exactly am I supposed to ask in the final then? अगर मैं f is equal to ma भी निकाल दूँ. Okay, so anyway, so keep that in mind, okay, that you should, that this should be essentially be a piece of cake for you. This should be bread and butter, okay? Easy, straightforward, you should be very comfortable with this, okay? So let's deal with the simplest case. कि आपने acceleration vector से जाना है position vector की तरफ. What's the simplest non-trivial acceleration vector that you can think of? Mathematically, a constant. Because previous आपको सर आपने position vector तो constant नहीं लिया था. Well, वो इसलिए नहीं लिया था कि position vector, if the position vector is constant, then the motion is absolutely trivial. Then there is no motion. But the acceleration vector being constant, well, that still can lead to non-trivial motion. Okay, especially when you're dealing with vectors. A physical example in which the acceleration vector is constant is gravity, essentially projectile motion. Essentially the motion of something that is moving under the influence of a constant gravitational field. So if you throw something near the surface of the earth, the acceleration vector, what's the magnitude of the acceleration vector? Okay, okay, I'll take it as 10 meters per second square. What's the direction of the acceleration vector? It's always towards the surface of the earth because you're dealing with near the surface of the earth. If you were Hercules and threw the rock, this assumption wouldn't be true. Okay? So you're always dealing with near the surface of the earth. Okay? So as a concrete example, you are standing on horizontal ground and you take some object and you shoot it. Or you take some ball and you throw it, you bring a cannon and you fire a cannon, okay, whatever. Okay? So you shoot some object, you put your friend in a cannon and fire him, okay, whatever. Okay? ठीक है? आपकी तो काफ़ी जो है वो लड़ाइयाँ नहीं होंगी because I've removed assignments. तो this urge won't start. Okay? आपके सीनियर्स को ग्रुप्स में असाइनमेंट्स में encourage करता था कि ग्रुप्स में करो असाइनमेंट, सीखो एक दूसरे से. ऑफ कोर्स वो सीखते नहीं थे, छापे मार रहे होते थे और ऊपर से जो है वो लड़ाइयाँ भी बहुत हो रही होती थी, पूरी कैट फाइटिंग चल रही होती थी. सर उसने काम नहीं किया, सारा क्रेडिट ले गया है, उसको उतने ही नंबर क्यों मिल रहे हैं, and so on and so forth. So then maybe you know the urge would have been much greater to shoot somebody in a cannon, okay, but not over here, okay. So anyway, so hopefully you don't do that, but anyway, so the acceleration is constant. That means that first of all, let's work out what the velocity vector will be when the acceleration vector is constant, what the position vector will be when the acceleration vector is constant. So the acceleration vector is constant. Then what is the velocity vector? Well, dv is equal to a dt. And we have already seen that this is v minus u equals the integral of a with respect to time. But a over here is constant. So a goes outside the integral. Look at integral kidhar hai. There you go. This a goes outside the integral. This is from 0 to t. This is from the initial velocity to the final velocity. You can put a prime over here, put a prime over here if you want to be very precise. This a goes outside the integral and you're left with a times t. Exactly the same as your good old v is equal to u plus at, except that you have arrows on top. Okay, so for constant acceleration, the velocity vector at time t equals the initial velocity vector time plus the acceleration vector times t. Sir, acceleration positive hai ya negative hai? That question is completely meaningless. Because you're talking first of all not about the vector being positive or negative, you should be talking about the component positive hai ya negative hai. That component being positive or negative depends on how you set up your axis. The acceleration vector for this case will always be like that. So if you make your y-axis pointing upwards, then the component of the acceleration is negative. But if your y-axis is pointing downwards, which is an equally valid choice, the acceleration vector component is positive. So don't ask me whether a vector is positive or not. It depends on the choice of your coordinate system. That question is meaningless. It goes back to that the vector cannot be equal to a number. A component of a vector is a number. Okay. Anyway, so with this, that v is equal to u plus at, that gives me a recipe to figure out the velocity vector. What's the recipe to figure out the position vector? Well, you go to v is equal to dr by dt, and therefore dr is equal to v dt. You integrate both sides. what do you get on the left hand side? R minus R naught, the change in the position vector. R naught is the initial position vector. This is equal to, over here plug in this, exactly what you did in 1D. ये इधर plug in करो, u plus at के ऊपर integrate करोगे तो क्या आएगा? ut plus half at square. Or the only difference of course that you are dealing with vectors now. So you have that. So you have v is equal to u plus at and you have r is equal to r naught plus ut plus half at square. Nothing really new over here. The only difference of course being, sir, either x or x naught नहीं नजर आ रहा, वो इसलिए नहीं नजर आ रहा because you have written down the position vector in terms of r rather than x. Okay, now let's apply this to our projectile problem. Okay, this is basically the part where I was relying on you कि ये तो खुद से पढ़ लोगे, but of course you know I might as well have said something else. Okay, but anyway, okay, so you have, we want to apply, the first question that we could ask is, where is the projectile sometime later? The object that I have thrown, where is it sometime later? Of course, to answer that question I need to specify how the object was thrown. So typically that is done in terms of the speed with which the object is thrown and the direction in which it was thrown at. So you specify the magnitude of the initial velocity, that is u, and the angle that the initial velocity vector makes with the horizontal. You could have chosen the angle that it makes with the vertical, of course that choice is equally valid. If you know this angle, you know the other angle. Okay. So this essentially specifies the initial velocity vector. I should note that this theta is constant. This theta is just the angle that the initial velocity vector makes with the horizontal. As the object flies, and you all know that it follows a parabolic trajectory, and you will see why, this angle that the velocity vector makes with the horizontal keeps on changing. But this theta is not that angle. This theta is just the angle that the initial velocity vector makes with the horizontal. That's it. That's a constant. Because once you have shot the object, that angle is not going to change. Okay. So anyway, so write down to apply this or to apply this, you just need to figure out what is r naught, what is u, what is a. To write, so you have to write down these vectors. So first of all, I have to write down the initial position vector, as in I have to write down the vector that describes the position from which the object was shot, from which the object was thrown. That description of course depends on where I place the origin of my coordinate system. You always choose the origin of your coordinate system in such a way that this vector becomes 0. Okay, so you place your origin of your coordinate system slam bang over here from where the object was shot. So that the objective of doing that of course is that it just leads to simpler mathematics. This r naught becomes 0, just like you did for circular motion. The simplest choice is to choose as your origin the center of your circular path. So this vector becomes 0 with this choice of your origin of coordinate system. I haven't chosen the axis yet. Now choose the axis. What should be the direction of your axis? Okay. Now the acceleration vector of course physically is always pointing vertically downwards. So you usually choose your axis in such a way that you have as many zero components of your vectors as possible. If you choose your usual axis, if you choose your axis like this, the acceleration vector only has a y component, it doesn't have an x component. If you had chosen a tilted axis, your acceleration of course would have both an x component and a y component. That is an equally valid choice, except that if you choose your tilted axis, you are also in trouble in another way. The description of the description of this ground is more complicated in your tilted axis, because right now what's the mathematical description of ground level? Y equals 0. क्या कोई position vector का y coordinate 0 है तो वो ground पे है projectile. It's as simple as that. If you use a tilted axis में आपका y coordinate 0 नहीं होना ground पे. Okay, so the condition, the mathematical condition of the projectile coming back and hitting the ground becomes much more complicated with a tilted coordinate system. Of course, if you're solving this problem on a slanted hill, as it has been done in the readings, which I also asked you to do, but nobody bothered to open them up, क्योंकि chemistry का quiz था या CS के हम coding आ रहे थे, okay, whatever, okay. 4 credit are, okay. That's all I'm going to say, okay. So, if you were shooting this projectile on a hill, the tilted coordinate system would probably be better. Because then the description of the projectile coming back and hitting the hill would be much simpler. Anyway, so with this choice of coordinate system, what's your initial velocity vector? Batao bhai. How do I write down the initial velocity vector? Jaldi batao. Oh, in terms of u and theta, yaar. See, it's easy. U cos theta Ex plus U sin theta Ey. What's the acceleration vector? The acceleration vector at any instant of time for this projectile. Projectile is anything that experiences only the acceleration due to free fall. So something that goes straight up and comes back down, that's also a projectile. उस केस में बस थीटा जो है 90 डिग्रीज है. ओके, सो ये भी होता है कि सर ये तो ऊपर फेंका, ये कैसे प्रोजेक्टाइल है? जब तक मुझे पैराबोला नहीं नजर आएगा नहीं प्रोजेक्टाइल हो सकता. ओके, आई मीन स्ट्रेट लाइन लाइक दैट इज आल्सो अ स्पेशल केस ऑफ पैराबोला, बस बहुत चिपका हुआ है. ओके, सो एनीवे, सो यू हैव द एक्सलेरेशन वेक्टर इक्वल्स नेगेटिव जी वाई. अगर आपका इधर कोई दरख्त पे बंदर लटका हुआ है उल्टा, उसने एक्सिस नीचे की तरफ पॉइंट की हुई है, तो उसका प्लस जी ई वाई आएगा, लेकिन उसका इनिशियल वेलोसिटी वेक्टर भी डिफरेंट होगा. उसका इनिशियल वेलोसिटी वेक्टर में माइनस यू साइन थीटा होगा अगर उसकी वाई एक्सिस उल्टी है. ओके, सो द साइंस विल एसेंशियली टेक केयर ऑफ ईच अदर व्हेन यू चेंज योर कोऑर्डिनेट सिस्टम. इफ द साइन ऑफ वन वेक्टर, वन component changes, when you switch your coordinate system, some other sign is going to change somewhere else, such that you get the same physical answer. ये नहीं होना कि बंदर के मुताबिक स्पेस में चला जाएगा प्रोजेक्टाइल, जो कि होता रहता है इस कोर्स में. स्पेस में क्या और भी बड़ी बड़ी अजीब अजीब चीजें होती हैं. 2 बिलियन बॉल कोलाइड करते हैं तो स्पेस में चले जाते हैं. ओके, ओके, सो देन और क्या चीज आपको चाहिए अप्लाई? आर नॉट हमने फिगर आउट कर लिया, यू फिगर आउट कर लिया, ए फिगर आउट कर लिया, बल्ले बल्ले हो गया. सो आर नॉट इक्वल 0, and all you have to do now is just plug it in. R of t equals R naught plus R naught is 0, never mind that. Ut, this vector times t, which gives you u cos theta times t Ex plus u sin theta times t Ey, and then you have this half a t square. अब देखो एडवांटेज यही हुआ है, देखो इधर में सिंपल सी चीज आएगी मेरे पास with this choice of the coordinate system, because the acceleration only has one non-zero component. So you just get minus half gt square Ey. Okay, so much for that. Now let's just rearrange this as usual. It's always nice to group together the x components, group together the y components. And what do you get? R of t will be equal to u cos theta times t Ex plus u sin theta times t minus half gt square Ey. This gives you the x coordinate, this gives you the y coordinate. Again, check your answer. How will you check your answer? Is at t is equal to 0, is your object at the origin? Putting t is equal to 0, ये 0 हो गया, ये 0 हो गया, ये भी 0 हो गया. Okay, so that works out. Are you getting the correct velocity vector from this? How do you get the velocity vector from this thing? You differentiate it. You get u cos theta. Theta constant है, remember. आपके जो illustrious seniors हैं वो इधर चेन रूल भी लगा के बैठे होते हैं. सर इसका डेरिवेटिव होगा u तो कांस्टेंट है वो बैठ जाएगा, फिर हम प्रोडक्ट रूल लगाते हैं. cos थीटा को बाहर रखें, t को डिफरेंशिएट करें, प्लस cos थीटा को डिफरेंशिएट करें, t को वैसे का वैसे रखें, और फिर थीटा क्योंकि फंक्शन है वो माइनस साइन थीटा डी थीटा बाई डी टी आ रहा होता है, पता नहीं क्या क्या लिख रहे होते हैं। ओके और फिर कहते हैं सर आपने टाइम बहुत कम दिया था। ओके मैं कहा आपका दिमाग भी बहुत कम है। ओके बट एनीवे ओके so you have, so remember theta is a constant, okay, over here with respect to time. So if you differentiate this with respect to time, you get u cos theta plus u sin theta minus gt. अब अच्छा ये साइड पे रखो, अब इसको अप्लाई करो, इसके मुताबिक वेलोसिटी वेक्टर क्या आ रहा है, u cos theta ex plus u sin theta ey minus gt ey. Exactly the same thing that you get by differentiating that. Okay. Then check whether it makes further physical sense. हाँ. ये तो उधर से आया हाफ एटी स्क्वायर से। हाँ y एक्सिस, यस, तो सिर्फ एक्सेशन सिर्फ y कॉम्पोनेंट है। Okay. Okay, so if I now ask you at what time does the projectile come and hit the ground again, वो कैसे निकालोगे? You have to learn how to translate these mathematical equations to the physical statements and vice versa. What does it mathematically mean that the projectile is at ground level? Y, आपके coordinate system में y equals 0, as in this has to be equal to 0. So you get u sin theta times t minus half gt square equals 0. And from this, don't divide by t, factor out t, that means that either t is equal to 0, of course, the object was at the ground level when you shot the object, or t equals, basically when u sin theta minus half gt equals 0. And that gives you t is equal to, क्या? 2u sin theta divided by g. So in other words, t को factor out कर लो, आपके पास आ जाएगा u sin theta minus half gt equals 0. या ये 0 है या ये 0 है. If you use that this is 0, you solve for t, you get that. So this is the so-called, इसको आपने of course याद किया होगा, ये capital T है. The time of flight, देखा नाम सारे आते हैं. Okay. If you know the name of 10 different bird species, doesn't mean that you know about the behavior of the birds. Okay, you just have given them 10 different names. Okay. क्या चीज? Because ground level, आपका ground level पे देखो क्या है. For every point on the ground, the y coordinate is 0. तो ये अगर ग्राउंड को जाके हिट कर रहा है, अगर अच्छा जब ग्राउंड ये सपोज को यहां जा रहा है, जब ये हिट करने लगा है उसको, द पोजीशन वेक्टर इज दैट. व्हाट्स द y component of this pink arrow? Draw arrows. This is the total time of flight. So this expression, by the way, this position vector of course breaks down when you go to a time bigger than 2u sin theta over g. Because after this time क्या होगा position vector object का? वही का वही, वो ऑब्जेक्ट प्रिज्यूमेबली उधर ही आके, अगर रेत है खास तौर पे, इधर ही आके फंस गया होगा जो आपने फेंका है. सो आपकी डेरिवेशन में क्या चीज ब्रेक अप हुई है? व्हाट ब्रोक डाउन इन योर मैथमेटिकल डेरिवेशन ऑफ दिस पोजीशन वेक्टर, कि ये टाइम कैपिटल टी के बाद ये गलत आंसर दे रहा है आपको. द एक्सलेरेशन वेक्टर इज नो लॉन्गर माइनस जी ई वाई. आपकी ये पूरा वेक्टर ही रिलाई कर रहा है कि आपका एक्सलेरेशन वेक्टर माइनस जी ई वाई के बराबर है. वंस द ऑब्जेक्ट हिट्स द ग्राउंड एक्सर्ट्स अ लार्ज अपवर्ड फोर्स ऑन द ऑब्जेक्ट. आपके एक्सलेरेशन माइनस जी ई वाई फिर नहीं है. वंस द ऑब्जेक्ट इज स्टेशनरी ऑन द ग्राउंड, द एक्सलेरेशन ऑफ द ऑब्जेक्ट इज 0. एक्सलेरेशन माइनस जी ई वाई रह ही नहीं गई, तो ये किधर से अप्लाई होता है?